Data analysis often involves dealing with messy, real-world datasets where missing values are a common occurrence. These missing values, represented as blank spaces or NaNs, can significantly impact the accuracy and reliability of our analysis if not handled properly. Understanding the nature of missing data is the first step towards addressing this challenge. There are generally three types of missing data: missing completely at random, missing at random, and missing not at random. Missing completely at random is the simplest case, where the probability of data being missing is completely independent of both observed and unobserved data. Imagine surveying students about their favorite ice cream flavor, but some forget to mention their age. This missing age data is likely missing completely at random. Missing at random implies that the missingness is related to some observed data but not the missing data itself. For instance, in a survey about income, people with higher incomes might be less likely to disclose their earnings, creating a missing at random scenario. Missing not at random is the most complex type, where the probability of missingness depends on the missing values themselves. Imagine a survey about health conditions where people with a specific illness are less likely to report it due to stigma. This missing data is missing not at random. Determining the type of missing data is crucial as it dictates the appropriate handling methods and affects the validity of our conclusions. Misunderstanding the nature of missing values can lead to biased results and misleading interpretations. Therefore, it's essential to carefully examine the dataset and the data collection process to make informed assumptions about the type of missingness we are dealing with. This understanding lays the foundation for choosing the most effective strategies to handle missing data and ensure the robustness of our analysis. Before we can fix missing data, we need to know where it's hiding. Detecting missing values might seem straightforward, but it involves more than just spotting blank cells in a spreadsheet. Effective detection requires a combination of visual inspection and programmatic approaches to understand the extent and pattern of missingness. The first step is often a visual scan of the dataset. This can be as simple as scrolling through a spreadsheet or using histograms and heat maps to highlight missing data points. Visualizations provide a quick overview of which variables are affected and whether the missingness appears random or concentrated in specific areas. However, visual inspection alone can be insufficient, especially for large datasets. This is where programmatic methods come in handy. We can use programming languages like Python or R to calculate the percentage of missing values for each variable. This gives us a quantitative measure of the missingness and helps identify variables with a higher proportion of missing data that might require special attention. Furthermore, exploring the relationship between missing values and other variables is crucial. For example, we can check if missing values in one variable are associated with specific values in another variable. These investigations provide valuable insights into the nature and potential causes of missingness, guiding us towards the most appropriate handling techniques. Having identified the missing values in our dataset, the next step is to decide how to handle them. While deleting rows with missing data might seem like an easy solution, it can lead to a significant loss of information, especially if the missingness is not random. Imputation methods offer a way to fill in these gaps, allowing us to retain the complete dataset and potentially improve the accuracy of our analysis. One of the simplest imputation methods is replacing missing values with a measure of central tendency from the available data. This could be the mean, median, or mode, depending on the nature of the variable and the distribution of the data. For instance, if we have a dataset of student heights and some values are missing, we can replace them with the average height of the remaining students. While mean, median, and mode imputation are easy to implement, they come with limitations. They tend to reduce the variability in the data and might not be suitable for all types of variables or missingness patterns. For example, Using the mean to impute missing income values in a dataset with a skewed distribution could lead to underestimation of the actual average income. Despite their simplicity, these methods provide a starting point for handling missing data. They are particularly useful when the amount of missing data is relatively small and the dataset is large enough to provide reliable estimates for imputation. However, for more complex scenarios, exploring advanced imputation techniques might be necessary to ensure the accuracy and reliability of our analysis. While simple imputation methods like mean and median can be useful, they often fall short when dealing with complex datasets and intricate missingness patterns. Advanced imputation techniques leverage the power of machine learning and statistical modeling to provide more accurate and sophisticated ways of filling in the gaps. Two prominent examples of such techniques are k-nearest neighbors, KNN, imputation and iterative imputation. KNN imputation borrows the concept of nearest neighbors to estimate missing values. It identifies k data points in the dataset closest in similarity to the one with missing values. The missing value is then imputed using the average of the corresponding values from these k neighbors. This method captures relationships between variables, making it more robust than simple mean imputation, especially when dealing with correlated features. Iterative imputation takes a model-based approach. It treats each variable with missing values as a dependent variable and uses the remaining variables as predictors to build a regression model. The missing values are then predicted using this model. This process is iterated multiple times, refining the imputation with each iteration as the model learns from the imputed values. Methods like MICE, multivariate imputation by chained equations, fall under this category. The choice between these advanced methods and simpler ones depends on several factors, including the nature of the data, the amount of missingness, and the computational resources available. While KNN imputation is relatively straightforward to implement, it can be computationally expensive for large datasets. Iterative methods, while potentially more accurate, require careful model selection and validation. Understanding the strengths and limitations of each method is crucial for making an informed decision and ensuring the reliability of the imputed data.